We're gonna we're gonna pick up right where we left off yesterday. So if you would, um, so we're at the bottom of the second page, and we got to the point where we were talking about component form, and we used like the magnitude and the direction angle to find the original vector, or we used the original vector in component form to find the magnitude and the direction, and we came up with a couple of formulas. So we came up with this formula right here. So if we've got a vector in component form, a comma b, in those angle brackets, we can find the magnitude of the vector, in other words, just how long it is, so that's a scalar, how long it is by squaring the horizontal component, squaring the vertical component, adding them together, taking the square root. So it's just an application of the Pythagorean theorem. And then we talked about how we can find the direction angle using tangent inverse. But we've got this little caution right here, this little asterisk, which means when you do that, your calculator is going to give you a reference angle, or at least the size of a reference angle. And then you've got to stop and think, okay, which quadrant am I in, and how can I use that reference angle to figure out what the direction angle is? Okay, so make sure you're careful with those. And then we talked about how we can do a geometric representation. We can actually draw pictures of these vectors and how we can do arithmetic with them. So how we can do scalar multiplication, how we can make them twice as long, how we can add them, how we can subtract them. And we talked about the tail to tip method, the parallelogram method, and then we also talked about component form. Component form is really nice, okay, because you don't have to worry about graphing it correctly or anything like that. I mean, you should always have some idea in which direction it's pointed, roughly how long it is and stuff like that. But finding this answer in component form is a lot easier than drawing this one, okay, starting at the origin, going to right here, then taking v because we're going to add v, and then add here. So we go from the tail of the first one to the tip of the second one. And then if we do the parallelogram method, I make a copy of u here and here. I make a copy of v here and here. So really we draw the two in standard position, okay, as position vectors. And then we make copies, and the resultant, remember that's kind of a weird word, but the resultant goes from the tail of both of them, in other words, from the origin to the tip of where both of them meet. You get the same answer either way, but it's an important thing to be able to do. Okay? Any questions there? Okay, so let's just double check and make sure that we got this one right. So we started with u, so there's u right there, and again u was 2 comma 3, so over 2 and up 3, horizontal component of 2, vertical component of 3. And then we're going to subtract 2 v's. So that means I do a minus 5 plus 2, so back 5 and up 2, another one, back 5 and up 2, and then the resultant right here, so I'll draw this one, this is u minus 2v. And we want to figure out what that vector is. So we could go through and count. Now remember, we were over 2 and up 3, and I went back all together, I would have gone back 10. So that should put me at negative 8 comma something else. And if I was up 3 and I went up 2 twice, that should put me at 7. Whoops. Sometimes I'll do that. Okay, so that should be the answer. And again, the easiest way to do this problem is to say, look, I'm going to take 2 comma 3, and I'm going to subtract 2 of 5 comma negative 2. And if I do that, I have 2 comma 3. And I like distributing the negative through, although it doesn't matter. So I'm going to write plus negative 10, comma, distribute the negative through, that's going to be a positive 4. And then when I put those together, I'm just adding horizontal components and adding vertical components. So I end up with 2 minus 10, that's negative 8. 3 plus 4, that's 7. So I get the same answer as I would over here. Okay, any questions there? You have some problems on your assignment, and we'll practice a few of these where they literally want you to draw them. Okay, and I'll show you again on some of those examples. Okay, are there any questions? Okay, at the bottom of the page, it says, look back at example 3 and notice that the original vector is the sum of the blank and the blank components. So let's go back to example 3. So that's this example right here, and I'm going to blow that up just a little bit. Okay, So the original vector was from -2, -1 to 2, 4, and we drew that one. And then we moved it so that it was a position vector, or sometimes again we'll call it a radius vector. So what I want you to notice is this vector right here is the sum of, if I were to take this vector, just a strictly horizontal vector of 4, 0. So go to the right 4, don't go up or down. And I took this other vector, go straight up 5, so this would be 0, 5. If I took the two of those and I add those together, don't I get this vector of, so if I add those guys together, that's a 4. Add those guys together, that's a 5. Doesn't that make the original vector 4, 5? Okay? So this idea of horizontal and vertical components is really important. It's kind of like compartmentalizing the direction of the motion and stuff like that. That's a really important skill to have. Okay, any questions? Perfect. Okay, so it's the sum of the horizontal and vertical components. Oh, and where did I have that typo? Didn't I have a typo in here the other day? Where was that? Bottom of page 1. Okay, I'll fix that one. Thank you very much. Okay, go ahead and flip over to this side right here. This is a copy of some properties of vector addition and scalar multiplication, and we'll just talk about these pretty quickly. They're relatively easy to work with, and then we'll kind of cover the last topic in this section and then do some problems from the assignment. So if we've got 3 different vectors, u, v, and w, and c and d are scalars, so remember those are plain old numbers. Okay. What this means is if I take vector u and add v, I get exactly the same as if I take v and I add u. Okay, so it kind of works like regular old numbers do. I can change the order. Does anybody remember that the name for that? Commutative. Okay, so vector addition is commutative, just like regular addition is commutative. Okay, this is called the associative property. If we're adding these 3 vectors together, it doesn't matter whether I add these 2 together and then add w, or take this one and add v and w to it. Doesn't make any difference. If we add the 0 vector, it doesn't change the vector at all. If I take a vector and add the opposite, what do I get? I get 0. Okay. And if I've got scalar multiplication, it doesn't matter whether I do c times du or cd and then times it by u, I'm going to get the same answer there. Okay, this is kind of like, what would this be called? Kind of like distributing. Okay, and then the same thing here. And then if I multiply a vector by 1, I get the exact same vector. And if I multiply it by 0, I get the 0 vector. And if I want to find, what does this mean again? Okay, you could think about it as absolute value, but we had a special name for it. Magnitude. Okay, absolute value is the distance something is from 0. Okay, you could think of the magnitude of the vector as the distance the tip is from 0, and it can be in any direction. Okay, so if I take a scalar and multiply it by a vector and find the magnitude, it's the same thing as finding the magnitude of the original vector and then just timesing that length, that magnitude, by the scalar. Okay, does that make sense? Those are pretty easy. Okay, so let's talk about something that's going to be really useful in the long run. Anybody in here that's going to go into engineering, especially electrical engineering and stuff like that, these are really important, okay? So we're going to talk about unit vectors, okay? So a unit vector, and I'm missing a little line right here. A unit vector is exactly what you'd think it is. A unit vector is a vector that is, or that are, 1 unit in length. So any vector that's 1 unit long is called a unit vector. And then we've got what we call the standard unit vectors. And those vectors are I and j. And I looks like this. I is 1, 0. And j is 0, 1. So this is strictly a horizontal vector. In fact, the way it's written right here as the standard unit vector, it's just heading 1 unit to the right. And this is strictly a vertical unit, okay, a vertical vector. It's got 1 unit going in the vertical direction, okay? So let's talk real briefly about why on earth we'd want to have unit vectors, okay? So the first thing is they provide us a coordinate system and a standard notation. So we've kind of been working on the XY plane, or thinking of it that way. If we have standard unit vectors I and j, we're going to call this the I-axis, and this will be called the j-axis. So they give us a coordinate system. So we don't have to worry, hey, are we working with x's and y's, or are we working with vectors? Okay, if it's i's and j's, we know that we're working with vectors. Okay, the next thing is unit vectors in common directions are easily recognized. So let me show you an example of this. Is that a unit vector? And which direction is it headed? Northeast, right? A little bit more north than east. Can you tell me what the direction angle is? 60, okay? That's a point on the unit circle, right? So this would be heading off like this. I've got one, whoops, let me have my computer catch up here. So I've got 1/2 here in the horizontal direction, and I've got radical 3/2 in the vertical direction. If I put the two of those vectors together, that's going to be a point on the unit circle. If this is 1/2 and that's radical 3/2, the magnitude would have to be 1. There's a unit vector. So if I've got a unit vector that's headed in one of those common directions, it's really easy to tell, okay? And we use those quite often. The next thing is we can rewrite any vector using the standard unit vectors. So if I've got this vector right here, one way that I can write that is I could write it this. I could write it, it's 5i's plus, whoops, minus 2j's. Because if you think about it, if I want 5, -2, that would be 5 this way and then down 2. So I could do 1, 2, 3, 4, 5 i's, and then minus 2 j's, and this would be the resultant 5, -2. Okay? So that's called a sum of the standard unit vectors. Okay? Vectors that are 1 unit in length are easy to work with. Okay? They give us the direction, which like in this example is pretty easy to tell, and they're easy to change the magnitude. So let's say I wanted one that was pointed in this direction, but I wanted it to be, let's say I wanted it to be 7 units in length. How long is it right now? 1. How could I make it so it's 7 units long? Times it by 7. So what I could do here is I could take this one and I could say 7/2, comma, 7 radical 3/2. Because what I did is I took that one and I did a 7 as a scalar out in front. Whoops, 3, 2. I mean, you can tell that's a unit vector headed at an angle of 60 degrees. It's 1 unit long, and if I want to make it 7, I just times it by 7 and distribute that through. Easily recognized, even if you factored the 7 out, makes it really easy to recognize. Make sense? Okay. And the last one, you'll just have to take my word for it. Unit vectors come in handy when we're doing like 3rd semester calculus, and they come in handy in higher mathematics, okay? So that's another good reason to know them. Okay, hopefully those first 4 reasons are enough, but if you don't buy those, then they're useful in higher mathematics, okay? Any questions? Okay, let's take a look at example 8. Okay, number 8 says, write vector v, which is 4, -3, as a linear combination of I and j, and then draw a geometric representation of the linear combination. Okay? So, does that sound hard? Okay. If you got what I said in those 5 things that we were talking about, this should be really easy. Okay? And if it's not, all we need to do is tweak a couple of quick things, and we're all set to go. All it's saying is, as a linear combination, write this in terms of i's and j's. So this would be 4 i's minus 3 j's. That's it. That's a linear combination. That's how easy it is. If it says draw a geometric representation of that, we want to indicate that we're taking 4 i's and then we're subtracting 3 j's. So we do 1, 2, 3, 4 i's. There's an I, there's an I, there's an I, and there's an I. And then I want to subtract 3 j's. So remember, the minus is going to change the direction of j. The positive j direction is going up, so we're going to go down 1, 2, 3. So there's a minus j, there's a minus j, and there's a minus j. And then here's the resultant. Again, from the tail of the first one to the tip of the last one, this is going to be 4 i's minus 3 j's. That's what it would look like. Okay? Any questions? Okay, how about the second part? Find a unit vector in the direction of v. Find a unit vector in the direction of v. Okay, it's heading off in this direction. It's not one of those that's easily recognizable, so it's not a 30, 60, 90, 45, anything like that. Okay? How long is it right now? And how would you figure out how long it is? Oh, you know, come on. What's that? Pythagorean theorem, or that little formula that said, look, if you've got a vector and it looks like this, if it's in component form, then the magnitude of that vector is going to be a big square root, and we're going to have 4 squared plus negative 3 squared, so we end up with the square root of 25, which is 5, right? So how long is that vector right now? 5 units long. So stop and think about this for just a second. If it's 5 units long right now, and I want it to head in exactly the same direction, but I only want it to be 1 unit long, how could I take that vector, or if you want to think of it in component form like this, how could I take that vector and make it so it's only 1 unit long? Divided by 5, right? So let's do 1/5, 1 over the magnitude times 4 comma negative 3. And we end up with this vector, 4/5 comma negative 3/5. Unit vector in direction of that guy right there. It's that simple. If you have the original vector, if you want to make it 1 unit long, all you need to do is find the magnitude and divide it by the magnitude, or multiply it by 1 over the magnitude if you wanted to think of it that way. Everybody good there? Okay, so let me just show you what this would look like. I'm going to zoom in on this for just a second. It's 4/5 comma negative 3/5. So 4/5 would be about right here, and negative 3/5 would be about right there. Wouldn't that put us on the same direction? Wouldn't that work? Okay. All right, you got a couple problems that ask you to do that. And then you've got a couple problems that ask you to do some pretty darn easy things like this. It literally says, it's got a picture and it says, draw these vectors. So if this is A and this is B, I'm going to take B. Now, whether you like the parallelogram method, the tail to tip method, I don't really care. I'm going to take B and I'm going to make a copy of it and I'm going to put it up here. So I'm going to take the tail of this one and start it right here. And I'd normally go over 5 and up 2. So I'm going to go over 5 and up 2. So here's a copy of B. And here's the resultant. Remember, it goes from the tail of the first one to the tip of the second one. And you can see how easy it would be to make this into the parallelogram method right here. Because all I'd have to do is draw a quick copy of A. A is over 1 and up 3. Over 1 and up 3. So it'll look like that. Okay, again, it's this diagonal. Please don't mix that up. Please don't do this diagonal. A lot of times people will do that. They'll just draw a vector from the tip of one to the tip of the other. Remember, you don't mix tips. You mix tails and tips. Okay? Any questions? Okay, would you draw this one then, please? Two A's minus a B. 2 A's minus a B. pretty easy, isn't it? It's not bad. So the second A would look like this, right? So there's another A. And then the minus B is going to be, instead of going to the right 5 and up 2, a minus B would be back 5 and down 2. So back 5 and down 2 would be here. Okay, so here's a minus B. And then where is the answer? From the tail of the very first one to the tip of the last one. So it's right here. Now, I think the instructions in the textbook just say draw it, so you might need to do a little bit of copying and stuff like that. Okay, and it is actually, I mean, to some extent, you have to do a little bit of drawing on these because it does kind of solidify the idea. Okay, if I said, what is the answer to each one of these? On a graph, what would we need to do? You'd have to count, right? So we'd have to go 1, 2, 3, 4, 5, 6, and up 1, 2, 3, 4, 5. So the answer on this one would be 6, 5. The answer on this one would be back 3 and up 4, so that would be negative 3, 4. Okay? Any questions? Okay. Do we need to do this one, or do you get the idea? Go ahead and do it? Okay, let's go ahead and do it. So we need to do a B minus 2 A's. So we need to do a B. B is going to be the first vector. And then from that, we're going to subtract 2 A's. Or subtract an A that's been made twice as long as it usually is. So here's the B, and then I'm going to subtract 2A. So instead of going to the right one and up 3, I'm going to go back 1 and down 3, like this. Back 1 and down 3, like this. So there's a minus A, and there's a minus A. And the resultant, again, from the tail of the first one to the tip of the second one, there's the answer right there. So if I had to count this off, I'm going to end up with, let's see, 3, negative 4. Is that right? Okay. I want you to take a look at this. Whoops. Okay, what do those two vector addition or vector subtraction problems have to do with each other? Okay, they're the same vectors, right? We just moved them, moved the order. Okay. Is subtraction commutative? Not here and not even with regular numbers. Okay? All right. So good point there. Any questions? Okay, so the cool thing about the next couple of problems is you'll notice that these are written in, so we've got these in component form, and we've got these written in terms of the standard unit vectors i's and j's. So let's just make sure we do these right. This one says take r and subtract s plus t. So if I take r, I'm going to take 3, negative 2, and I'm going to subtract s plus t. So that's going to be negative 1, 5 plus 4, negative 6. So that's going to be 3, negative 2. If I put the two of these together, I get negative 3, negative 1. And then if you want to do the subtraction, so what I did here is I added those together, right? Did I write them down right? We doing okay? Okay. So if I add those together, this is the vector that I get. If I want to do subtraction and I want to do negative 3, negative 1, that's totally okay. If I wanted to distribute this through and make it addition, that would be okay also. Yeah. Did I write something down right? Oh, yes, yes, thank you. Yep, thanks. Very good. It's Monday, right?
Yeah.
Thank you. Close. Yeah, really close. Okay, good? Okay, so I can do the subtraction this way, or if I wanted to distribute this through and then make it addition, that's fine. Either way, you're going to end up with, what's the first component? What's the horizontal component? 0. And what's the vertical component? It'd be -1. Okay? So if it's written in component form with the angle brackets, you probably ought to write the answer in component form. The cool thing is, if we're working with these guys right here, it's kind of like working with regular old variables. Okay? The rules are very similar. So if I were going to do this problem right here, I'd do 2 times 2i minus 5j minus 3 times v, and v is -3i, and you guys keep me honest, make sure I don't make any silly mistakes here. So it's just like working with variables. So this is going to be 4i minus 10j plus 9i minus 12j. So when I put all these together, I get 13 i's and I get minus 22 j's. That's it. What does this mean in terms of horizontal and vertical? 13 units to the right and 22 units down. And could we quickly convert something like this into i's and j's? Same thing back and forth, okay? So either way. Okay, any questions? Okay, we're going to look at 2 applications of vectors. And then if we've got time, we're going to take a look at a few problems from the assignment and make sure we're in good shape there. So I'm going to blow this up just a little bit. I think you've got plenty of room here. We've got a couple people in here that have had physics before, and if you've had physics before, you're at an advantage because you've probably done problems like this. So here's what we've got. A 600-pound force is required to pull a boat and a trailer up a ramp inclined at 15 degrees from the horizontal. Okay, so they didn't show so we've got a boat and a trailer. So if we're going to pull this boat and the trailer, we've got to pull with a force of 600 pounds. Okay, hopefully we've got a truck to help us do that. Okay, it says find the combined weight of the boat and the trailer. So here's how this works. Okay, this is called an inclined plane problem, and I'm going to simplify this just a little bit. Okay, I'm going to draw another picture right here. Here's the ramp. This is 15 degrees. And to make this a little bit easier, we're going to picture this as just a block. This has some block that has some weight. And to make things easier, we ignore friction and stuff like that. Okay? So here's what happens. When we have something that weighs whatever amount, that weight goes directly toward the center of the earth. It goes straight down vertically. Okay? I'm going to make that a little bit shorter. I'm going to make it do this. Okay? But when it's on a ramp, I mean, imagine we oiled this up, or say this was a block of ice or something like that. Okay? If we put this on the ramp, let's say it was like a nice sheet of metal or something like that, and we put a block of ice that weighs 30 pounds on here, what's going to happen to the block of ice? It's going to slide down. Okay? So part of it wants to slide down this direction here. Okay? Now, what if I had a really, really steep ramp? Okay, what if I had one that was this steep and I put the block of ice on it? Would it slide down faster or slower or the same as this ramp right here? Faster. In fact, if I've got this really extreme and had a ramp that was straight up and down, I don't have a ramp anymore and it would just fall straight down, right? Okay, so what happens is this weight gets broken into 2 different forces, okay? This is the force that wants it to slide down the ramp, and then there's another force that's called the normal force, and it is perpendicular to the ramp. It's kind of the part that keeps it stuck to the ramp. So what happens here is this vector represents the weight. This vector represents the force that wants it to slide down the ramp. And this vector right here, okay, I'm going to use an N for normal, okay, that's the one that keeps it stuck to the ramp. And the steeper the ramp is, okay, the smaller that normal force is that wants to keep it toward the ramp, and the bigger the force is that wants to make it slide down the ramp, okay? So let's take this picture right here and think about what we've got going on right here. Okay, since this is a right angle, just like that's a right angle, we've got a couple right angles here. Okay, this angle down here is going to be exactly the same as this angle for the ramp. So if this is 15 degrees, that's going to be 15 degrees. So here's what I've got. I have a triangle that looks like this. That's 90 degrees. That's 15 degrees. This is the weight. This is the normal force. And this is the one that's making it slide down the ramp. Now, on this particular problem, did they tell us how big any of these vectors would be? Where would the 600 go on here? 600 is the answer to one of these. Where would the 600 go? It is Peyton? Okay, Peyton is so certain that it's X. Now, can you say that again?
X.
All right, that's very certain. Okay, it is X. Okay, so think about what's happening here. It says the force required to pull a boat up the ramp. So we're pulling on the ramp this way. Notice how that's parallel with the ramp. It's the same as this force that wants to make it slide down the ramp. Okay, so in order to keep it in its place, and we simplify this just a little bit, if we were pulling with exactly 600 pounds, that would keep it right where it is. But in order to make it go up, we have to pull with just slightly more than that. Okay, so we kind of ignore that part. Okay, so that force that's wanting to slide down the ramp is 600 pounds. Okay, that's the piece that we know right here in this picture. So if that is 600 pounds, what are they asking for here? They're asking for the weight. They're asking for the combined weight of the trailer and the boat. Okay? Now, imagine we talked about what you're going to do over the weekend for a bit, how much sleep you're getting, what your favorite movie is and stuff like that. And then we looked at this problem right here and ignored everything over here and just looked at this right here. Is there enough information to figure out everything on that triangle? Yeah, there is. Do we need to figure out everything? No. What do we need? All we need is W. W is the only thing we need. And we have the opposite side, and we need the hypotenuse. What trig function? Sine. Okay, good try. Sine of 15 degrees equals opposite, which is 600, over the hypotenuse, which is W. Now, before you type that into the calculator, I want you to think for just a second. Okay, if we're pulling it up a ramp with a force of 600 pounds, okay, now do ramps make pulling easier? So we're basically lifting something up. Do they make lifting something up easier or harder? Easier, okay? So we're expecting the weight of this boat in the trailer to be more or less than 600? More than 600, because it only takes 600 pounds to pull it up the ramp. If we were lifting it up to get it up to, whatever height we needed to get it to, that would be really hard, okay? So ramps help us lift things up gradually, okay? What is the answer to this? 2318.2. Sounds about right, okay? That's probably in the ballpark for how much a boat and a trailer would weigh. Okay, any questions? Sure? Okay. Many times, this problem was given backwards. Many times they'll do something like this. So let me change this problem just slightly. Let's say I have a 30-degree ramp, and let's say that I've got a box on here for some strange reason that I want to pull up there, and I'm telling you that the box weighs 4,000 pounds. Very heavy box, and we're probably not going to be able to move it, but there's no friction because we're mathematicians and we like to make things easy. Okay? I could ask you two questions. I could say, what is the force that would make this slide down the ramp? Or in other words, how hard would you have to pull to make it go up the ramp? And I could also ask, what's the normal force? Okay? These meet at right angles. The normal force is perpendicular to the ramp. This is 4,000. What do I need on this triangle right here in order to be able to solve this? You need what? You need an angle. And which angle do we know? We know the one down here. You know that one's 30 degrees. Okay? Can anybody tell us why that one has to be 30 degrees? Okay, here's why. Okay, and it would help if I did this. Put it right on there. This is 30 degrees, and this is 90 degrees. This is 60 degrees, correct? This is up and down, and that's up and down. These are both vertical. So if they intersect the same line and that's 60 degrees, doesn't this have to be 60 degrees? So if that's 90 and that's 60, what's left for this one right here? Okay, you can go through that logic every time, or when you draw these, and you'll notice that I drew this triangle different than the way they drew their triangle. I like it looking like that for some reason. To me, it makes more sense, okay? If you wanted to draw it like this and draw the triangle down here, that's totally okay. I just like it like that. Okay, just realize the one down at this point right here, that angle is going to represent the exact same angle as what the ramp is. Good? Okay, last type of problem I want to show you, and I guarantee you're going to see these again. These are used all the time. This is a problem out of your book, and I didn't realize that I copied the answer down, or at least part of the answer, so pretend like you can't see this. Okay, I'll cover that up in just a second. Hopefully we get that same answer there. Okay, so I'm going to show you how to do this two different ways, and I don't care which way you do it. I'm going to advocate for component form because I think in the long run that's more useful, but I'll show you a different way to do it that you may like better, and then I'll tell you don't use it. Okay. An airplane is traveling at a fixed altitude with a negligible wind velocity, so it's basically flying through still air. Okay, the airplane is headed north 30 degrees west at a speed of 500 miles an hour. North 30 degrees west. Okay, so you'll notice that what they've done here is they've taken that 30-degree difference there and they've figured out from standard position what would that be. Okay, so that's going to be our 120. So if you think about it, to this point right here, if I stop right there, they have given me a magnitude and a direction. If I have a magnitude and a direction, what do I have? I've got a vector. Okay? So they tell me that the magnitude for the plane is 500 and the direction angle is 120 degrees. So if I wanted to talk about the vector P representing the plane, look back in your notes. Wasn't there a way where we could quickly just write down, oh, it's just this times this, comma, this times this? What did the horizontal component have to do with, and what did the vertical component have to do with? And in the right order, cosine and sine, right? Okay, so we had this little formula that said the vector would be theta, the magnitude times the cosine of the angle, comma, the magnitude times the sine of the angle. So this is going to be 500 times the cosine of 120 and 500 times the sine of 120. That's the airplane, right? That sentence to right there gives us a vector for the airplane. It's going a certain speed in a certain direction, so we can represent that with a vector. Are there any questions there? Okay, let's read the next part. As the airplane reaches a certain point, it encounters a wind with a velocity of 70 miles per hour. So it's giving us a speed, it's telling us how fast it's going, in the direction of north 45 degrees east. Okay, now, they didn't give you this, so we're going to do this over here. Let's talk about the wind. Let's draw a picture like this for the wind. There's the plane, let's draw the wind. The wind is north 45 degrees east. So it's going to deviate from north by 45 degrees, and it is 70 miles per hour. So from standard position, what's the angle from standard position? Happens to be 45, so that's nice and easy on this one. So the magnitude for the wind is 70. The direction angle is 45. So could I come up with a vector for the wind? You bet. 70 cosine 45, comma 70 sine 45. Now, were they pretty nice on this problem? They were pretty nice, weren't they? Okay, because these are angles that we know the value of sine and cosine. What if this was 122 degrees? Calculator. If this was 46 degrees? Calculator. Okay? As it is, I'm going to write down, let's see, cosine 120, correct me if I'm wrong, but that would be negative 1/2. Right? So this is going to be negative 250, comma, cosine 120. Cosine of 120 is positive radical 3 over 2, so this is going to be 250 radical 3. Did I say that right? Good there? Okay. And the wind? Radical 2 over 2, radical 2 over 2. So this is going to be 35 radical 2, comma, 35 radical 2. Good? Okay, any questions about how we found the vector, the component vectors for the plane or the wind? Okay. Okay, who's flown in an airplane? Who's flown in a small airplane? Okay, a couple of you. Have you ever, so you looking out the windshield when you're landing? Okay, if it's windy, are you pointed straight at the runway? No, you have to kind of angle off a little bit, right? Okay, so what happens is, that's called a drift angle. What happens here is this. This is the vector that represents the plane, and the wind does this. It pushes it off in this direction. Well, you'll notice you've got a tail and a tip, and a tail and a tip. So what's the resultant? It gets blown off course, which is what we're after right here. Okay, so that's where this picture comes from. This is 500. This is 70. What we're interested in figuring out is, all right, you got blown off course. Did that speed you up or slow you down? How did the wind affect your speed, your ground speed? And you're not going to be heading at 120 anymore. You're going to be heading somewhere else. Okay? So here's what we're going to do. Let's take the plane and add the wind and see what we get. If I take the plane and add the wind, I get negative 250 plus 35 radical 2, comma, 250 radical 3 plus 35 radical 2. Now, those are kind of ugly numbers, and we're certainly not going to finish with this. So let's figure out, okay, so this is the resultant. Could you get some decimals for me, please? So I need negative 250 plus 35 radical 2, and I need 250 radical 3 plus 35 radical 2. Anybody got the horizontal? Negative 200.5. Okay. Somebody confirm that? Is that right? Okay, got that. And how about the 250 radical 3 plus 35 radical 2? 482.5. Everybody good there? Okay. That is the vector for where the plane is actually headed. What do we want to know about it? If you were in the airplane, if you were piloting that aircraft, what would you want to know? I want to know my vector. And my vector has two parts to it. How fast am I going as far as I'm concerned? What's the magnitude and what's the direction? What direction am I actually heading so I can correct that a little bit? Does that make sense? Okay, so how do we find the magnitude? Must be Saturday already for you guys. Okay. Use that formula. Square the horizontal component, negative 200.5 quantity squared, 482.5 quantity squared. That'll tell us how fast we're going, and if you type that in, we'll get a number right there. And then I also want to know what is the direction. So I'm going to use tangent inverse of the vertical over the horizontal. And I've got a negative in there. You got that in there? Can somebody tell me how fast the plane's going? Is it this one?
Yeah, sorry. 438.87.
438.87. Is that right? Yes? Okay, so 438.87, and that would be in miles per hour. Oops. What about the angle? What'd you get? Negative 67.43. Okay, is that the answer they got? Okay, whenever I do that theta equals tangent inverse, I would really like it if you put something right here just as a reminder. What did we put right here in our formula? We put an asterisk. Why? Because that's the reference angle. Okay, that's how big the reference angle is. Reference angles are always formed with which axis? The x-axis. So if you look on here, this angle right here is 67.43. How do I figure out what it is from standard position? 180 minus that. And what is 180 minus that? What is it? 112, whoops, 112.6. Okay? So those are the two things now. What if I said this? I want you to do north something west. So we give the directions, the bearings in the same system that they gave it to us in. How far did we deviate? Subtract 90 from this and it should be 22.6. 22.6 degrees west. Okay? Okay, now are there any questions about that? Okay, let's double check ourselves. So I'm going to back up here just a little bit. Oops, if I can get there. I need to change the size of this PDF. Okay, there's that. They got this. I'd like to double check that. I was a little surprised when it came in. Yeah. If you plug that in correctly, you should get 522. And let's go back here and take a look at this and think about why this would have to be longer. Okay? If that heads off in this direction right here, it's actually helping it just a little bit. It's a tiny bit of a tailwind, even though it's coming from the side, mostly from the side. Okay? So it is going to be longer. So could somebody double check that? Okay, is it right? What is it again? 522.5. Okay, so make sure you're careful typing that in the calculator. And then I want to show you one more thing. There's a problem on the assignment that I'm going to make extra credit. So for those of you that like to challenge yourselves, it is, I think you can do all of them except for, it's on the next page. Okay, and I think you can figure this one out. You can find videos on YouTube. You could go to Khan Academy. You could go a lot of different places. This is called, I think it's called a static load. And what we've got here is a vector heading down, that's 2,000 pounds, and it gets split on two cables. Okay, and you can figure out what that load would have to be and what that load would have to be by breaking it up like this. And if this isn't going anywhere, these two would have to be exactly the same. They'd have to amount to the same. And this one right here, I'll call this one y1 and this one y2. What would those two have to equal if you added them together? If they're going to support that 2,000-pound load, and this is pulling vertically and this is pulling vertically, if you add them together, what would they have to equal? They'd have to equal 2,000. Okay? You have to solve a system of equations in order to get that, but they're really interesting problems. I wouldn't put one on a test, but for those of you that want to challenge yourselves, we'll call number 74 extra credit, okay? Or sorry, 75 extra credit. But I got to see all the work and everything, and then I'll give you extra double credit or extra credit for number 76 if you can do that one, okay? All right, any questions? Okay, have a great weekend. Yeah, it's, remember, if you didn't write it down the other day, it's on the website, okay? So the assignment for 6-3 is on the website.